For all the incredible leaps we've seen in AI, particularly with these massive language models flexing their reasoning muscle, a persistent challenge for you, someone always tracking the cutting edge, is how to actually deploy and use that power efficiently.
Yeah.
It feels like we're constantly navigating this trade-off between, top-tier intelligence and the practicalities of speed and cost, right?
That's a really insightful way to frame it, definitely. The deeper the reasoning capabilities we demand from AI, the more complex and frankly resource intensive the underlying models tend to be,
Right.
especially when it comes to generating responses, what we call inference. This has been, well, a fundamental bottleneck as we aim for increasingly sophisticated real-world AI applications.
Well, that perfectly sets the stage for our deep dive today, NVIDIA's Nemotron-H family of language models.
Uh-huh.
Now, these aren't just another set of LLMs hitting the scene. What's really grabbed my attention, digging through their technical reports, is the genuinely novel hybrid Mamba-Transformer architecture they've pioneered.
Yes, that's the core of it.
It looks like a very deliberate attempt to tackle this exact dilemma, balancing high accuracy with efficient operation. Our mission today is to unpack the core academic innovations here, the specific architectural choices, and the, well, novel techniques they've employed to achieve this balance.
Exactly. The central innovation of Nemotron-H lies in its strategic divergence from a purely transformer-based architecture.
Okay.
To truly appreciate the significance of this, we probably need to briefly revisit the self-attention mechanism. That's been the bedrock of most advanced language models, the concept laid out by Baswani and colleagues originally.
Okay, let's unpack that foundational piece. Self-attention, yeah, it's been the workhorse for these models, letting them weigh the relevance of different parts of an input when processing info.
Right.
But where does this crucial mechanism hit a wall when it comes to efficiency, particularly during inference, like when the model is actually generating text for us or answering queries?
So the crux of the issue is how self-attention scales, specifically with the length of the sequence it's processing.
Right.
Imagine having to check back at every single word you've already said to decide on the next one. The longer the sentence, the more checking you have to do.
Okay.
Similarly, for each new word a transformer model generates, the self-attention layer's computations increase linearly with the number of preceding words. It also needs to maintain this KV cache, essentially a memory of past computations,
Okay.
which also grows linearly. Now, think about those complex reasoning tasks that, OpenAI and DeepSeek AI research highlights. To achieve those nuanced, high-quality outputs, the model might need to process and generate really long sequences internally, and that linear increase in computation and memory, it can become a significant bottleneck. It just slows things down and needs a lot of resources.
Right. So longer context equals lower processing and higher memory demands. That paints a clear picture. Now, this is where Mamba comes into the picture, isn't it?
Exactly.
It's been generating some buzz as a potentially more efficient approach.
Precisely. Developed by Gu and Dao, Mamba offers a fundamentally different paradigm for sequence modeling.
How so?
Unlike self-attention, Mamba's computational cost and memory footprint remain remarkably constant for each new token generated. It doesn't matter how long the overall sequence is.
Constant, regardless of length.
Yes, which offers a substantial theoretical advantage, especially when dealing with very long contexts where, traditional transformers can become really unwieldy.
Constant computation and memory, wow, that sounds like a real breakthrough for those long, complex inference tasks we were just talking about.
It is potentially, yes.
So did the Nemotron-H team just swap out the transformer blocks wholesale for Mamba and, call it a day?
Not at all. And this is where the core academic contribution, the real innovation of Nemotron-H truly shines. They've adopted a hybrid architectural approach.
Hybrid, okay.
So rather than a complete replacement, they've strategically integrated Mamba 2 layers with a relatively small proportion. It's around 8% of conventional self-attention and MLP layers.
Only 8%.
Roughly, yes. If you look at Figure 2 and Table 1 in their technical reports, you can see the specific configurations they used for their 8 billion and 56 billion parameter models. It clearly shows this carefully considered blend.
Okay, only about 8% attention layers? That seems surprisingly low. What's the academic thinking, the rationale behind this hybrid design? Why not lean more heavily or even just go all in on Mamba, given its efficiency benefits?
Well, the reasoning here is grounded in a growing body of research, including some influential work by Waldef and collaborators.
Ah, okay.
These studies have shown that hybrid models, the ones that thoughtfully combine transformer elements with more efficient sequence modeling alternatives, can actually achieve surprisingly competitive accuracy on various tasks, compared to pure transformer architectures, I mean.
Interesting.
So the Nemotron-H team's approach isn't just like a simple mix and match, it's a deliberate architectural choice. They want to exploit the efficiencies of Mamba for the bulk of the sequence processing, especially for managing those long dependencies.
Right, the constant cost aspect.
Exactly, but they strategically keep a small number of self-attention layers. This likely lets the model still capture certain types of complex, maybe more global interactions within the data that transformers are really good at.
So finding the sweet spot.
Precisely. The key innovation lies in identifying this optimal balance, maximizing inference throughput without taking a big hit on model accuracy.
Okay, that makes perfect sense. A very strategic fusion to leverage the strengths of both. Now, the technical reports also put a lot of emphasis on their advancements in creating high-quality pre-training data.
Oh, definitely.
It seems clear that architectural innovation isn't the whole story, is it? The data you train these models on is just as critical.
Absolutely. And NVIDIA has made some substantial academic contributions here in refining the pre-training data pipeline for Nemotron-H. They developed the Nemotron CC11 dataset, which comes from the huge Common Crawl web data.
Okay.
But what's particularly noteworthy from a research angle is their sophisticated method for data curation. They used an ensemble of diverse model-based classifiers to rigorously sort the massive amount of web data into these granular quality tiers.
So not just quantity, but really grading the quality.
Exactly. It allows for a much more nuanced approach to selecting data, letting them prioritize the higher quality sources. And what's more, they explored using synthetic data generation techniques to sort of intelligently denoise the lower quality bits and boost the overall diversity of the training set.
Ah, interesting. Using AI to clean up the data for AI.
Pretty much. And Table 2 and Figure 3 in the reports show some compelling quantitative evidence. They illustrate the better quality distribution of Nemotron CC11 and how it positively impacts model performance compared to other data sets like DCLMs and FineWeb Edu.
So a move beyond just hoarding data towards, well, actively curating and improving the training material. And this phased pre-training strategy they used, what's the thinking there?
Right, this phased data blending approach, which Feng and co-authors detailed, is another significant research contribution.
Mm-hmm.
They structured the pre-training into 4 distinct, carefully planned phases. Each phase has a specific mix of training data sources. You can see it visualized in Figure 4.
Okay, 4 phases.
The first phase strategically emphasizes exposure to a really broad spectrum of diverse data. Then the later phases progressively prioritize high-quality, more curated data sets.
Building up the quality over time?
Kind of, yeah. The idea is the model first develops a broad understanding of language in the world, and then it refined its knowledge and reasoning by seeing more pristine information. Their empirical results showed this phased approach gave a measurable boost in final model performance compared to just using the same data in a random order.
So curriculum learning, basically.
Exactly. It highlights the importance of that concept in this context.
It sounds like a very thoughtful, academically driven way to train, building that strong foundation first. Now, you mentioned the 56B model was the first trained using this novel FP8 recipe.
That's right.
That sounds like a significant step for training efficiency. Can you elaborate what is FP8 and why is this new recipe noteworthy research-wise?
Sure. So FP8 refers to a family of 8-bit floating point numerical formats.
Okay, 8-bit.
Yeah, using these lower precision formats means more computationally efficient matrix math, and it significantly cuts down memory bandwidth needs during training compared to, say, 16-bit BF16 or standard 32-bit floats.
Big savings potential.
Huge. NVIDIA developed a novel FP8 per tensor current scaling recipe. And the Nemotron-H 56B base model is indeed the first in the family fully pre-trained with this technique.
Per tensor scaling.
Right. The per tensor part means they apply dynamic quantivation, choosing the best scaling factor individually for each tensor. It adapts to the range of values within each one. They also strategically use different FP8 formats, E4M3 for weights and activations, and E5M2 for gradients during backpropagation.
Different formats for different parts. Interesting.
Yeah, and interestingly, to keep things numerically stable, especially in the first and last layers, they actually kept using BF16 for the first and last 4 GMs, the matrix multiplications.
Ah, a bit of a hybrid approach, even in the number formats.
You could say that. Figure 5 in their report shows the training loss compared to a BF16 baseline, and Figure 6 provides pretty compelling evidence. Despite maybe a slightly higher initial loss, the FP8 trained model ultimately got comparable, sometimes even better, downstream task accuracy than the BF16 version.
Wow.
It's a really significant step forward in making training these extremely large models more accessible and, frankly, more efficient.
So more compact numbers, faster training, less memory, but crucially, without hurting the final model quality. That's a major contribution to scale training. Okay, let's switch gears a bit and delve into mini puzzle. That sounds like an exciting innovation focused on model compression for deployment.
Mini Puzzle definitely represents NVIDIA's novel and, I think, academically significant framework for model compression. It cleverly integrates and builds upon their earlier research, things like Minitron and Puzzle.
Okay?
The main research goal here is to develop ways to create smaller, more resource-efficient versions of the models, versions that can actually run within the tight memory constraints of specific hardware, like fitting onto a single GPU.
Right, making them practical.
Exactly. This is super critical for enabling longer context inference and just broader accessibility of these advanced models in different real-world scenarios.
Okay, so how does mini puzzle actually shrink the model? What are the key algorithmic stages?
It uses a pretty sophisticated three-stage pipeline. Stage 1 is importance estimation.
Okay, finding what matters most.
Basically, yeah. The framework rigorously analyzes the pre-trained model to figure out the relative importance of its various parts, specifically individual layers and neurons within the feed-forward networks, the FFNs.
How does it measure importance?
They use a computationally smart approach. It looks at the impact of these components during forward passes with representative data to estimate how much they contribute to the model's overall performance. Interestingly, their research showed that directly pruning Mamba heads or their internal dimensions really hurt accuracy.
Okay.
So they strategically focused their pruning efforts on removing entire layers and individual neurons within those FFN layers. Figure 9 in the report actually visualizes these calculated layer importance scores for the 56B model.
Makes sense to identify the less critical parts to chop out selectively. What's stage 2?
Stage 2 is conditional neural architecture search, or NNES.
Searching for the best smaller structure.
Exactly. Using the important scores from Stage 1, Mini Puzzle systematically explores the huge space of possible pruned architectures that fit the user's memory constraint. In their experiments, they specifically targeted a 32 GB GPU, like an RTX 5090, aiming for efficient FP4 inference.
Okay.
The algorithm iteratively checks different combinations, how many layers to keep, what size the SFN hidden dimensions should be, and selects the most promising candidates using lightweight proxy metrics that correlate well with the original model's performance.
Clever.
Figure 10 shows a performance versus memory trade-off curve for different pruned options, and Figure 11 visually shows which layers got removed in some of the best smaller models.
So an intelligent search to find the best mini network within the hardware limits. And the final stage must be about tuning that compressed model.
Precisely. The third and final stage is knowledge distillation.
Teaching the small model from the big one.
That's the idea. After the structural pruning, the smaller student model gets trained further by learning from the output behavior of the larger, more accurate teacher model, the original 56B model in this case.
How does that teaching work?
They use logic-based distillation. It focuses on making the students' predictions match the teacher's, not just for the correct answer, but across the whole probability distribution of possible answers. It helps the student learn the teacher's relative confidence.
Okay, learning the nuances.
Exactly. Table 6 shows the performance of several pruned models before and after this distillation, which helps pick the best one for a longer, more intensive distillation process, and the result is pretty remarkable.
Yeah.
They created a significantly smaller 47 billion parameter model that achieves accuracy very similar to the original 56B model, but it has a compelling 20% improvement in inference state and needed way less training data for the compression step,
Wow.
which makes it feasible to deploy on a single high-end GPU like the RPX 5090.
That's genuinely impressive, keeping almost the same accuracy but smaller, faster. That's a huge win for actually using these advanced models. And it's all thanks to this sophisticated mini puzzle framework.
It really is a significant piece of engineering and research.
Now, the Nemotron-H family also extends to vision language models, VLMs. How do these fit into the broader picture of their research contributions?
Right. The foundational Nemotron-H base models also serve as a really strong backbone for their vision language models. Nemotron-H8B VLM and Nemotron-H56B VLM.
Okay.
These models integrate the Nemotron-H language processing with a powerful vision encoder, specifically the Intern VT300M V2.5 model using the NVLMD architecture.
So combining vision and language.
Exactly. This architecture lets the models effectively process and reason about both text and images. These VLMs are particularly relevant for advanced multimodal AI applications. You see them used in the Cosmos Reason 1 project for sophisticated physical AI reasoning tasks, for example.
And Tables 7 and 8 in the reports provide empirical evidence showing their competitive performance on a range of standard vision language benchmarks. It demonstrates the generalizability and effectiveness of the underlying Nemotron-H foundation. So the efficiency gains and the high-quality training of the base Nemotron-H models carry over nicely into the more complex world of multimodal understanding.
It seems so, yes.
That really underscores the robustness and versatility of their core architectural innovations. And finally, the reports detail their work on instruction tuning and extending context handling. How adaptable are these Nemotron-H models for specific tasks and longer inputs?
Yeah, NVIDIA invested considerable research effort here, fine-tuning the Nemotron-H 8B base model to create Nemotron-H 8B Instruct. They had a dual focus, making it better at following complex instructions and also extending the length of context it can handle effectively.
Okay, instruction following and long context.
Right. They used a carefully designed three-stage fine-tuning pipeline. First, supervised fine-tuning, SFT, with datasets containing long context examples. Then, offline reinforcement learning from preferences, RPO, on a diverse set of instructions, both general and specialized. And finally, on-policy RPO that included safety-related data.
A multi-stage process.
Yes. And Table 9 shows strong performance for Nemotron H8B Instruct on various well-known instruction-following benchmarks. It shows it's effective at understanding and executing natural language instructions.
And the long context.
What's particularly interesting academically are its strong, long context capabilities. They evaluated it on the Tough Ruler benchmark that's in Table 10, and it achieves competitive performance even compared to pure transformer models that have significantly more attention layers.
Even with only 8% attention layers?
Exactly. Furthermore, there are internal ablation experiments where they compared the alignment of transformer versus their hybrid Nemotron-H models, detailed in tables 11 and 12, provide more empirical support. It really backs up the viability and, frankly, the significant potential of this hybrid architectural approach for building highly adaptable and performant language models.
Okay, so let's try to recap then. What are the most significant research contributions and key takeaways from this deep dive into the Nemotron-H family? It really feels like NVIDIA has pushed the boat out across several critical areas here.
Absolutely. I think the significance of Nemotron-H rests on several key academic and practical innovations. First and foremost is that novel hybrid Mamba-Transformer architecture.
Right, the efficiency focus.
Yes, it offers a compelling and, importantly, data-backed solution for significantly improving inference efficiency, which is a major bottleneck for deploying advanced AI widely without a huge compromise on accuracy.
Okay, point one, hybrid architecture for efficiency.
Second, there are rigorous advancements in data curation methods and the empirically validated phased pre-training strategy. It really underscores a sophisticated and effective approach to training these massive models.
Point two, smarter data and training.
Third, the successful development and application of their FP8 training recipe, that's a crucial research contribution towards making large-scale model development more efficient and scalable.
Point three, FP8 training efficiency.
And finally, the innovative mini-puzzle framework. It provides a powerful and efficient way to compress these large models so they can be deployed on resource-constrained hardware, which expands their accessibility.
Point four, mini puzzle for compression and deployment.
Right. These aren't just, small incremental improvements. They represent pretty substantial progress in the field.
And for you, the listener, constantly trying to understand the next wave of AI, these innovations have really profound implications. These incredibly powerful models, more efficient, more adaptable, and easier to deploy on a wider range of hardware, NVIDIA is essentially paving the way for faster, more accessible, and ultimately more impactful AI applications across countless domains.
Yeah.
It's a clear sign that the focus is shifting beyond just building ever larger models towards engineering smarter, more practical AI systems.
And this raises a really interesting research question for us to maybe chew on. Given Nemotron-H's proven ability to balance accuracy and efficiency with its hybrid architecture, how might this kind of carefully engineered hybrid approach fundamentally reshape the future of AI hardware and software co-design?
Oh, interesting thought.
And, as these inference bottlenecks continue to be reduced through innovations with these, what entirely new classes of AI-powered applications might become technically and economically feasible? Things we're perhaps only just beginning to imagine.
Some truly fascinating questions to consider, and for those of you eager to explore these advancements in more detail, NVIDIA has announced plans to release the Nemotron-H models on platforms like Hugging Face, Nemo, and Megatron LM in the near future.
Yeah, that'll be great for the community.
It provides an exciting opportunity to engage with this cutting-edge research firsthand. It's clear that these innovations are unlocking a wealth of exciting new possibilities in the evolution of artificial intelligence.